Hello everybody, this is Alex Swan again with the $0 MCAT course. Today we're going to discuss part 2 of the circulatory system, which is fluid dynamics of blood circulation. That is pretty much the physics of blood circulation. But before we dive into this topic, I'd like to review what we discussed in the previous video, which is part 1 of the circulatory system, and introduce some new concepts. And this diagram should look very familiar to you because I took it from the previous video. Let's just go over it one more time, right? Blood flows unidirectionally, right? In this diagram, it's flowing clockwise, right, throughout this circuit. And as with any closed circulatory system, right, blood will only flow unidirectionally. We can see that the right side of the heart is oxygen poor and CO2 rich, and the left side of the heart is oxygen rich and CO2 poor. And that's because the blood that goes into the pulmonary circuit is going to be enriched with oxygen, and the CO2 is going to be removed from the blood, and vice versa for blood at the systemic circuit. When I started this unit, I asked you what the purpose of the circulatory system was. And I said, there are obviously many correct answers for this. And we focused more on the circulation of blood right now, but we haven't focused so much on the role of the heart. So let's look at that more carefully, right? What we see very clearly here is that the heart separates oxygen poor and oxygen-rich blood. Right? This is actually not the case in all organisms, right? But in humans with the 4-chambered heart, closed circulation, double circuits, right? We have the separation of oxygen-poor and oxygen-rich blood. That's one function of the heart. But then you could also ask me, well, Alex, why does that actually need to occur? Because couldn't the blood that's right here in this pulmonary vein go straight to the systemic capillaries down here without returning to the heart? Right? We see that in some organisms, actually, this does occur. For example, in fish, right? We have blood that would return from the pulmonary capillaries, right? And it goes straight to the systemic capillaries, bypassing all of this stuff, right? That occurs in some organisms. And it works for them. But what's the advantage of blood passing again through the heart? Why is it that humans evolved hearts or circulatory systems that would take blood from this pulmonary circuit and bring it back to the heart before releasing it to the systemic circuit, right, and these systemic capillaries? Well, it turns out that another function of the heart besides the separation of oxygen-poor and oxygen-rich blood is pressurizing the blood. Right? We're going to go over this in the next video lecture, actually, in more detail, but the heart is a huge muscle. It's made up of cardiac muscle cells, right, to be distinguished from smooth muscle cells and skeletal muscle cells. But the heart is made up of cardiac muscle cells that are very, very strong and will pressurize blood right as soon as it leaves the heart at the ventricle, right? So in this graph, I'm going to show you blood that moves throughout the systemic circuit. Now, how do I know it's the systemic circuit? Well, because here my axis is labeled with aorta. I know that the aorta is the systemic artery, right? And we also have the vena cava here, and I know that the vena cava are the systemic veins. So this describes the systemic circuit, although it very well could describe the pulmonary circuit as well. The relationships would be similar, although the numbers probably would not be the same, but that's not super relevant for our purposes. Our purpose just concerns with the relationship between blood pressure and the position of blood throughout the circuit, right? As blood moves from a ventricle back to the atrium, right, through the arteries, the arterioles, the capillaries, the venules, and the veins, we can see that blood pressure continuously decreases, right? It's very, very high when blood leaves the left ventricle, or any ventricle for that matter, and that's because the blood is heavily pressurized right there. But then it falls as we go throughout the circuit, and eventually when we return to the heart, it has its lowest pressure. Now, you're going to ask me what the reason is for these spikes, right? You have these spikes here in the beginning of the graph when blood immediately leaves the ventricle. And I'm going to tell you not to worry about that for this moment. We're going to get back to that actually in the next video. So the point that I'm illustrating is that blood will lose pressure as it moves from the heart, right, throughout the circuit and then back to the heart. Now, what this means, right, is that this pressure is going to influence the exchange of nutrients and substances, right? If we go back to this slide, I mentioned that these capillary beds are essential because that's where nutrient exchange occurs. And it turns out that pressure dynamics are going to govern that exchange of nutrients, substances, and gases. As you can see, this diagram illustrates a typical capillary, right, in a capillary bed, right? This is a capillary. And the first thing I'm going to point out is that capillary beds have a sense of directionality to them, right? We're going to assume in this figure that that this used to be an artery, right? That an artery eventually existed far back here and then eventually branched off into that capillary. And then we're also going to assume that downstream of this end of the capillary bed, we're going to have a vein, right? This is obviously downstream and this is obviously upstream. And we're going to notice that there are two ends of the capillary bed, right? We're going to have an arterial end and a venous end, right? The end that is closer to the artery is called the arterial end. The end that is closer to the vein is called the venous end. And we have two different types of pressure gradients that exist across the wall of this capillary, right? We're going to have this hydrostatic pressure, and we're going to have this osmotic pressure. Now, hydrostatic pressure, as I mentioned up here, is the same thing as blood pressure. So why don't we return to the previous slide so that we can look at that more carefully, right? We're going to see that here, right, there I'm going to have my arterial end of the capillary bed. And right over here, right, we're going to have the venous end of the capillary bed. And we notice that the blood pressure is going to fall, right? It's going to fall from here, right, down to here once it reaches the venous end, right? So we have a decrease in the blood pressure. We have a decrease in the blood pressure as we move from the arterial end of the capillary bed to the venous end of the capillary bed. Now, as I mentioned, that blood pressure is pretty much synonymous with hydrostatic pressure, right? Hydrostatic pressure is the typical pressure that you think about when you think about liquids that are pressurized, right? It's the pressure that a liquid exerts against the walls of its container, especially when that liquid is or that fluid is very heavily pressurized. You have lots of hydrostatic pressure. And we can see that since blood has pressure, right? Apologies for that. Since blood has pressure, right, this hydrostatic pressure exists, but it's going to decrease, right? This hydrostatic pressure force, which describes how hard the blood pushes against the walls of the capillaries, that hydrostatic pressure is going to decrease, as you can see by the size of this red arrow, right, which becomes smaller and smaller and smaller as we move towards the venous end of the capillary bed. So the lesson here is that as we move down from the arterial end to the venous end of the capillary bed, right, we have a decrease in hydrostatic pressure. All right, we kind of beat that to death, right? So let me point out something else in this figure, which is obviously the osmotic pressure, right? We see that there is another force of pressure that counteracts this hydrostatic pressure force, and this is osmotic pressure. And we can see that it remains relatively constant as we move from the arterial end of the venous end, right? In fact, it's not just relatively constant, it is constant, right? And we also see that in this blood, right, we have not just these red blood cells, but we have albumin, right, which is a plasma protein. Now, it turns out that albumin, these proteins that I've drawn here, are essential in maintaining this osmotic pressure gradient. And how is that so? Well, first of all, what is osmotic pressure? Osmotic pressure is the pressure that results from a concentration gradient of a non-diffusible solute such as albumin. So let's say we have this inverted U tube right here, and let's say we put water into it, right? We put water into it, and then we insert this membrane, and this membrane is going to be permeable to water, but it's going to be impermeable to albumin. Now, why is that important? Because what we do later is we first take this U-tube, right? We fill it with water, we put that membrane there, and then on the right side of that U-tube, we're going to put albumin, right? And albumin is going to dissolve into that solution. And this is going to be the initial state, right? This is going to be immediately after we have this U-tube and we put albumin onto the right end, right, of that U-tube. What's going to happen, right, is obviously nature wants to exist in equilibrium, right, in terms of equilibrium concentrations, right? Here on the right side of this U-tube, we have a high concentration of albumin. Whereas here, right, the concentration of albumin is in fact 0, right, because we're taking these green dots to represent albumin. What's going to happen over time, right, and this is going to occur over time, not immediately, but it's going to occur over time, is fluids are going to move across this semi-permeable membrane in order to equalize this concentration gradient. Right? So what's eventually going to happen is we're going to have, since this albumin cannot move through this membrane, right, in order to equalize these concentrations, this high albumin concentration with this low concentration of albumin, we need to add water to the other side, right? So water is going to move from this side to the other side in an attempt to decrease this concentration of albumin, right? So we can see at equilibrium, right, and again, this figure is not really equilibrium, so I'm going to say equilibrium sort of, because in equilibrium, right, we would see essentially, all of the water here move here because there are essentially no albumin particles here, right? But that's kind of an artifact of this figure. The point that I'm trying to illustrate is that water will move across this semi-permeable membrane so that we can decrease the concentration of albumin. Right? And hopefully we can equalize these two sides of the semi-permeable membrane. That flow of water, right? What the water pushing through this membrane into this side of the U-tube in order to equalize the concentration of albumin, right? That movement of water, this movement of water is going to be called osmotic pressure, right? As the definition indicates, it results from a concentration gradient of a non-diffusible solute. And you can see that this membrane, right, does not permit the diffusion of albumin, probably because its pores are way too small. Now let's connect that back to the what occurs at a capillary bed, right? We see albumin, right? My apologies for that. Let's go back to the slide. We see albumin here, right? So clearly the concentration of albumin, right, in the blood is much higher than the concentration of albumin in this interstitial fluid. And the reason for that is because albumin is a large protein that does not readily diffuse through the pores of these capillaries. In an attempt to equalize the concentration gradient of albumin, right? Albumin is much less concentrated in the interstitial fluid than it is in the blood. What's going to occur is the fluid is going to exert this osmotic pressure force that's going to attempt to dilute the concentration, or it's going to attempt to dilute the blood in order to decrease the concentration of albumin, right? So as to equalize the concentration of albumin across this membrane. Obviously, since albumin is almost exclusively present in blood and not in the interstitial fluid, this concentration gradient is never fully equalized, right? And we're going to have this force of osmotic pressure that is going to be exerted, right, by the interstitial fluid against the walls of the capillaries. Now, why is the osmotic pressure force grade why is the osmotic pressure constant as we move from the arterial to the venous end? Well, because we're assuming, and this is probably most likely the case, that the concentration of albumin, right, is going to be constant throughout a capillary bed. Right, we're going to assume that the concentration of albumin is constant, and since osmotic pressure will depend almost exclusively on the concentration of albumin, right, the osmotic pressure is pretty much remains the same throughout this capillary bed. Now, what does this mean? As I told you, right, the hydrostatic pressure will decrease as we go from arterial to venous end. Osmotic pressure stays the same, right? So eventually we're going to reach a point near the venous end of the capillary bed, right, where the hydrostatic pressure has reached a minimum. Right? At the arterial end, that's where hydrostatic pressure is at a maximum. As we can see right here, the hydrostatic pressure, which I'm going to say is P sub H, is greater than the osmotic pressure P sub O. And because of this, what's going to happen is fluid is going to leave the blood, right? We're going to have a net filtration of fluid from the blood at the arterial end of the capillary, because this hydrostatic pressure that is pushing the fluid out of the blood is greater than the osmotic pressure, which would move fluid the other way. However, at the venous end, right, P sub H is less than P sub O. So what's going to happen is the fluid, right, this blood is not going to be pushing as hard against this capillary wall as the interstitial fluid is pushing against this capillary wall. So we're going to have actually some of the interstitial fluid that's going to be reabsorbed into the blood at the venous end of the capillary. And therefore we say we have a net reabsorption of blood which occurs at the venous end, right? So at the arterial end, we have the movement of fluid out of the blood, and at the venous end, we have the movement of fluid back into the blood. All right, now that we've covered that, we can talk about a little bit in more detail about the characteristics of the different types of blood vessels. Now, I told you that arteries and veins were different because they move blood in different directions. Right? Arteries will move blood from the heart to the capillaries. Veins will move blood from the capillaries to the heart. In this slide, right, I'm going to move back a few slides. we learned that the pressure of blood when it is in the arteries is much, much higher than the pressure of blood when it's in the veins, right? And it's for this reason that we have a very, very thick wall here in the arteries, as we can see, right? These arteries have this thick wall of smooth muscle and this thick layer of connective tissue. And the reason for that is so that the blood vessels, these arteries, can withstand the high pressure of the blood, since it's just leaving the heart and it's being very heavily pressurized, right? If it weren't for this, we would have these arteries that become ruptured, right? Now, as we go to the veins, right, we realize that the pressure of blood decreases as it's moved throughout the artery, through the arterioles to the capillaries, through the venules, and back to the vein, right? The pressure of blood is much lower. So since the pressure of blood is much lower, we don't need as much support for this valve, right? This layer of smooth muscle is going to be much thinner, right? And this layer of connective tissue, in fact, is actually going to be much thinner as well, right? So we have a thinner layer of smooth muscle and a thinner layer of connective tissue in the veins when we compare it to the smooth muscle and connective tissue of the arteries. In addition, we're going to notice that veins have these valves, right? And what are these valves for? Well, valves will only permit one-way flow of the blood, right? These will only permit one-way blood flow. Now, if we think about the previous slide, right, which showed the pressure relationships between blood and the arteries and the veins, right? The arteries have blood that is so heavily pressurized that it is definitely not going to move backwards, right? If you think about it, if you force a fluid through a vessel in such a high pressure, there's no way that fluid is going to travel backwards, right? And again, right, the characteristic of our circulatory system is that blood must flow in one direction, right? Blood cannot flow in both directions. So how do we maintain the flow of blood through these veins in one direction, right? The pressure of this blood has reduced so much that we need these valves to prevent blood from flowing backwards, right? We don't want blood to flow backwards through the veins and then through the capillaries, right? We want blood to go through the veins and then to the atrium of the heart, right? And that is achieved through this valve. So if we talk about the structural differences between arteries and veins, the major characteristics I want to point out are these thicker layers of smooth muscle and connective tissue in the arteries and the presence of valves in veins. Now, this is also from a previous lecture. I want you to recall the relationship between the size of these blood vessels and the number of blood vessels, right? Blood is going to flow obviously in this direction, right? This is going to be the flow of blood. Blood goes from arteries to arterioles to capillaries to venules and veins and back to the heart, right? And as we can see, we have these blood vessels that become much smaller, right, in size as we go towards the capillaries and become much bigger in size as we go from the capillaries to the veins, right? And we see the opposite relationship in terms of the number of blood vessels, right? We have lots of capillaries as compared to veins and arteries, both of which we don't have very much of. Now, what does this mean, right? A question I could ask you is, what does this mean about the total cross-sectional diameter, right? The total cross-sectional diameter of all of these different types of blood vessels. Well, that relationship is going to be depicted in this graph, right? We can see that there are so many capillaries, right? We have very few, just few arteries. We have more arterioles. We have lots of capillaries, right? These are these branched out networks of capillary beds. We have fewer venules than we do capillaries, and we have fewer veins than we do venules. And the total cross-sectional area peaks right, when we are at the capillary beds. Right? That's when the cross-sectional area is highest. Now, why is that important? Well, that's important because it's going to determine the velocity, right? So as we increase in the total cross-sectional area of the blood vessels, what's going to happen is the velocity of the blood is going to decrease, and eventually when the blood reaches these capillaries, right, the velocity of the blood is extremely slow. Now, what is the purpose, I should say, or why is it significant that the velocity of blood reaches its minimum when it is in the capillary beds? The reason for that is because, just think about it, we want nutrient exchange and solute exchange and gas exchange to occur at these capillary beds. So if we have blood that goes very, very fast from the arterial end of the capillary beds to the venous end of the capillary beds, then none of the nutrients are going to have enough time to exchange, right? In order for efficient exchange to occur, we need to ensure that blood moves through these capillary beds at an extremely slow velocity, and that's exactly what we see here, right? And part of that is because we have this increase, this huge increase in the total cross-sectional area of all the blood vessels, that the fluid is forced to slow down via physics, right, by the rules of physics, and we're going to get to that in a minute. Now I want to go back to this slide, but I want to point out another characteristic that is essential to the effective exchange of nutrients and substances in capillary beds. We saw that at the capillaries, right, the blood flow, the velocity of blood is at its minimum. What we also see here is that the walls of the capillaries are extremely thin, right? We have just this layer of endothelium in the capillaries. We don't have any smooth muscle like we do in the arteries or like we do in the veins. And we have these very, very, very thin walls, right? Even the endothelium isn't very thick. And that is going to promote the exchange of substances between the blood and the surrounding interstitial fluid, right? Because we have much thinner walls. So not only is the low velocity of the blood going to promote substance and solute exchange in the capillaries, but the thin walls of these capillaries is also going to promote that. So again, we're getting back to structural differences being related to functional differences. All right, now we're going to go back to this slide because I want to ask you several questions. The first question is, why doesn't the blood just stop mid-capillary, right? It looks like the velocity of blood here, right? It's probably not exactly zero, but it reaches very, very close to zero, right? Now, why doesn't the blood just stop there, right? Well, it's certainly not because of valves, right? Because valves don't exist in capillaries. They only exist in venules and veins. Certainly, it doesn't seem to make any sense why blood wouldn't just come to a full halt, right, when you're dealing with velocities this low. The reason for this is actually due to the pressure gradient, right? As we can see, the velocity of blood will approach zero, and it's going to come very close to zero when we get to the capillaries. But when we look at the pressure of blood, right, the pressure of blood doesn't even come close to zero, right? It comes closer to zero, but we still have a good amount of pressure, right, that exists in the blood as blood moves to the capillaries. Now, something that you may recall from physics is that fluids will move towards regions of lower pressure, right? Fluids move toward regions of lower pressure, and blood obviously is a fluid. And so what's going to occur is it's not the velocity of blood that is going to bring it to a halt in the capillaries, right? Blood actually doesn't do that. The lower pressure that exists here in these venules and these veins is going to be the driving force that moves blood from the arterial end of the capillary to the venous end, right? And then eventually through the venules and through the vena cava. Right, so it's the pressure that forces the blood to move through the capillaries and that prevents blood from coming to a halt. Now, the other question I want to ask you is, why does blood velocity increase, right? It's very clear why blood velocity decreases, right, as we go from the aorta to the capillaries. That's because we have a lot more capillaries, right? We have more numerous capillaries. We have a greater cross-sectional area. We have decrease in the blood pressure, right? But why does blood velocity increase? Well, to answer this, we're going to need to, again, invoke some physics. And if you remember from physics, we have this quantity that's called volume flow rate, right? And it's represented by A times V, where A is the total cross-sectional area of certain vessels, and V is the velocity of the fluid that moves through those closed vessels. And so let's just consider the relationship between the volume flow rate of blood that's here, right, and blood that's here, right? This is going to describe the volume flow rate of blood that's in the capillaries, and this is going to describe the volume flow rate of blood that's in the systemic veins. What we know is that this volume flow rate must remain constant. So since we have a decrease in the total cross-sectional area here, right, as we go from the capillaries to the veins, by the way, this A variable stands for total cross-sectional area, right? So as that variable decreases, right, as the value of this A in the veins decreases, right, what's going to need to come up to compensate for that decrease is the speed of blood in the veins has to increase, right? In order for this volume flow rate to remain constant, that's what must occur. Right, so the short answer is to my question, why does blood increase in velocity? The short answer to that is because the total cross-sectional area decreases. But the real answer is so that the fluid can maintain a constant volume flow rate. All right, and with that, we're going to end this video lecture. Thank you for watching this video. Our next video will focus on the cardiac cycle and its regulatory mechanisms. Hope to see you there.